far enough that you guys can start homework tonight and not think you would fall behind if you didn't. You'd just be on track with the sophomores who are going to have to catch up a little bit, but not a lot. Mostly just copying notes. So this is just a downwards parabola. We could go ahead, we could have found this maximum. Let's see. I just passed back that worksheet, right? Remember the one with the parabolas and the maximums and the minimums and completing the square? I just gave it to you. How could we have found the maximum of this on our own by hand? There are two ways. In the calculator, we can use the max feature, right? We can find the max. How could we have done it by hand? Do you remember? Two ways. One way is to get it into vertex form, which would have kind of been like last chapter, because didn't last chapter have a y minus k and an x minus h being squared for a parabola with a 4p? So how could you have gotten the h and the k? Just by completing the square. But to complete the square, wouldn't you have had to get a leading coefficient of 1? So to get a leading coefficient of 1, you would have had to pull out this negative 1 over 72, which would have made this minus 72, so that it could still be a 1. Anyway, so we could have done it by hand, or we could have done x equals negative b all over 2a. That would have worked also. Because your negative b would have been negative 1 all over 2a. 2 times negative 1 over 72 would be 1 over 36, and then flip it. Hey, 36 is exactly, well, remember the calculator has to approximate, so it got as close as it could. 35.99996, I don't even know. But really it's 36. But a couple things just real quick, making sure you guys are good. I have it in my graphing calculator, but question, in function mode, you just use the x variable button, no stress. You can play with your window, which is what we did, x min, x max, y min, y max. Why does my graph look like this and not that? What further adjustment did they make to make it all nice and you could actually count by things? The y and the x's, what do you mean? Because look, it's the same graph, so it had to be the same zoom, right? How did they have the nice tick marks? Do you remember which of these options changes the, good, the scale. The scale is what changes it. So from going from, what, to 100, they have 10, 20, 30, 40, yeah, I think they went by tens. So the scales, I mean, you can always change those just to give yourself some nice tick marks. It might make it a little bit nicer, a little bit easier. So then that's when, or that's how your graph can be a little bit nicer as far as 10, 20, 30, because there's no way you could count anything on this. It's so close together that it's solid. So that's pretty nifty. But then down here, we're like, hey, there's another way of talking about this. The rectangular equation only shows the path. I want you to start thinking about this as a path. Meaning it's like the path of motion of something, whether it's a particle, whether it's a baseball, whether it's a football, whether it's a some sort of projectile that's being like shot or flung, or what's something else that could go in a parabolic motion? Roller coaster? Anyway, think of this as the path. The problem is, though, if you just have the y and the x and the quadratic in terms of x, you don't know where something is at a certain time. All you can see is the path. Like a roller coaster, all you can see is the roller coaster. You can't really see where the cars are. Do you know what I mean? Have you guys ever driven past an amusement park and like seen the people on the ride and like seeing them actually moving on the ride? Rectangular form is just seeing the ride and never seeing the people on it, or never seeing like a specific position on the ride, just seeing the ride itself. So parametric mode says it might be helpful sometimes to actually be able to consider different placements on the ride, meaning after 5 seconds have passed, where are the people? After 10 seconds have happened, where are the people, etc. So it's not just looking at the ride, but it's looking at when, where something is, a particle or a person or an object, whatever's being, the ball that's being thrown, etc., where it is and when it is at that spot. So here's the extra variable, not just the where, the x, and the y, but the when, the t. And so when you guys are putting this in your parametric mode, you've noticed, hopefully, when I go to mode and change it to par. So far we've used function, that's y equals f of x. We've used sequence, that's the a of n one, or the u of n one. Par mode, when you guys went in, you realize that when you hit this little button, not function x, but parametric t. And guess what? Polar theta and sequence n. Anyway, when you plug this all in, double check really fast. Do you guys have the square root ending at the 2 and not being over the t? Just double check real quick. It's just a common mistake that happens every year.
Do you press alpha and then 4?
No. Use your variable button. It's a good idea. It is a t, but it's not the variable t. Does that make sense, Carl?
Oh, yeah.
So the programming is built on the variable t, so keep using your variable button.
All right.
It's in the programming, so you're good. So make sure that your square root stops. I had to kind of go back and change that. Make sure the square root stops. But otherwise, now all of a sudden we have x in terms of the horizontal position. X still means horizontal position. X still means how far over. That's okay. Y still means how far up or down. That's still vertical position. But the struggle is they're both dependent. X and Y are both dependent on t. Our new independent. So x and y both depend on t. So in these parametric equations, can you guys rewrite this for me? Can you write this first one, x of t? And can you write the bottom one, y of t? Like f of x. Same exact type of notation in the sense of the function of, but now x is a function of t, y is a function of t. So in parametric, you have this third variable t. Basically, you're splitting up the horizontal and vertical positions and dealing with them separately and not together. So think of it this way. You're not just thinking of the path. You're not just thinking of the path, but you're also thinking of, in parametric mode, the position at certain times. So you're not just thinking of the path, but you're also thinking of positions at particular times. Go ahead, Carl.
My calculator's being random. It's just doing this one.
Ooh, no, it's very possible. Let's go play with our window. Remember how I said you guys should look at your windows? Depending on what mode you're in, this parametric equation could be really funny. Now, over here you do have a certain window, and you might have actually put that in. But the problem is this window only works when you're in a certain mode, because parametric equations, believe it or not, the t actually kind of behaves sometimes like a theta. Because if you guys look over here and look at the different range, the t, that's not very much of a t range. And the reason is because this window that you see up here is using radians. Now, if you're in degree mode, this little baby range of t's might not be very sufficient. Now, I don't know exactly what my window is. I'm just going to hit the graph button right now. Ooh, mine worked quite well, except weird. It's missing the earlier tail. Why is it missing? Right? The parabola is supposed to go on forever, to the left and to the right. I don't understand. Let's go look at the window and say, what's weird? When does t start? 0. I wonder if I had let t go a little bit backwards and been like, hey, what was going on at -1? I wonder if it would graph anymore. Oh, it did. I wonder if I was to move my t and say, hey, I want to look only after, for instance, 1 second. Could have been 1 minute, could have been 1 hour, but after 1 second, where was this? Depending on t, I mean, you could even go ahead and technically make t something weird, like between 10 and 20 seconds. And you might not see anything. So one dilemma as to what you're seeing or not seeing could be time. Because you have to make sure that you're showing a time interval in order for the movement to happen. And the cool thing is by the original time interval, whatever it might be, you could actually do something like 2 pi if you want to think, since I'm in radians, I'm using small numbers. I was able to figure out by going negative and it went backwards by going positive, or an upward, a further time value beyond 0, like 1 or like 10. I was able to see that my position, my movement, is not just on this path, but it's also, check it, in this direction. These little arrows are called orientation arrows. If you guys haven't written them on your graph yet, go ahead and show them. You can think kind of like vectors. It's showing direction, but it's not showing direction in a line. It's showing direction on a curve, putting the x and y together, the x position and the y position together. So we need to show little orientation arrows anytime we have parametric equations. The t equals time is going to determine how many of the x's and y's are actually graphed. So when t equals 0, the particle was here, or the ball or the projectile was here. At t equals 3 root 2 over 4, the particle or the projectile was here. And then at t equals 3 root 2 over 2, the particle or the projectile was here, 72. Now, as you guys look at this, a couple things real quick. The nice thing is, number one, you're not going to have to make your own, make up your own parametric equations. You're not going to have to make up any parametric equations. You're just going to have to learn how to deal with them, how to work with them. So first of all, that's good news. You won't have to make it up. And second of all, this is where the timing comes in. It's when they made an equation for x. This is where the timing came in. And as soon as they made an equation for x, guys, look at your function, your rectangular equation. What was your rectangular equation?
1 plus
Negative x squared plus 72 over x.
That's over 7.
Oh, over 72? Let me get rid of this little box real quick. So check it. If we know what x is, couldn't we take the y equation and couldn't we substitute in to get it? So once we have the x equation, I mean, this looks a lot different, I know, but once we know what x is, in terms of t, we can plug into the x spot of the rectangular equation, we could get here. So this one actually just naturally flows out of doing a quick substitution of this x equation in. So this is where the timing is brought in, and then it's kind of transferred into the y. So just think, we're not just looking at the where, that would be up here, we're looking at the when as well. And that's what you guys see on the purpose statement. Now, that's just showing you a quick example of the differences in graphing, having you guys get a little bit used to it in your graphing calculator, et cetera, et cetera. But let's get back to the basics. So back to the basics, parametric equations. Let me zoom this out.
So I'm just doing really good with my graph, right?
Let me come look at it. My guess is your mode, degree or radian, does not match your T-min T-max. So your mode is radian, that's good. But your T-min to T-max, that's good, and that you have that being tiny. But the struggle is you're going by way too big of steps. Because in between 0 and 2, if you're going by 1.8, you're only going to have like 1 or 2 steps. You're only going to have 1 or 2 points. So I just did 1 or 2 points and connected. It wasn't looking in between. But if I said a lot more steps, like 0.1, there'd be a lot of 0.1s in between, right? But it's not that big. Your zoom is still a little bit. Oh, we had the n squared root. That's where I was in the beginning. Such a hard place. The n squared root and this one is root 2. There you go. Now it's okay.
Thank you.
Thanks for reminding me, Carl, because actually it's something that might go wrong in a calculator that I need to show them too. So we actually have x being a function of t, but as we showed the page before, we could just say x is t. Y is also a function of t, or we could just say y is t. Substitution is going to be a little weird. The path of a parametric set of equations, because now parametric equations come in pairs. You need the x and the y, or else you can't graph it on an xy plane. So parametric equations come in pairs. And the resulting path, here's a snazzy term for it. The path is called the plane curve. So if you're trying to sketch a parametric equation, remember there are pairs. We're just going back to the very beginning. In Algebra 1, if you learned to sketch something before we ever made you memorize parabolas and cubic functions and absolute value functions and sines and cosines, and before any of that, you would just make a table, right? So let's do that with parametric. We're going back to the very beginning of this whole new way of graphing, this whole new way of looking at things and defining them. So we're going to form a table where we can say, just for sake of simplicity, let's make it horizontal instead of vertical. Even though in Algebra 1 you probably always put your little table going down. We're going to have t's, the independent, and we're going to plug into x, and we're going to plug into y. And here's the weird thing. When you graph, you don't graph the t's. There is no place on an xy plane for a t. T t is just showing instead like the existence. So let's say something's moving from t equals 0 to t equals 7. Am I going to graph at t equals -1? No, because it's not a part of the situation. So the t value shows us whether or not he gets graphed. And then time, well, I guess this could be a hard question if you want to think very deeply and research a whole lot more than this class. Time only moves in what direction? Simply saying, forward. Exactly. So when we graph points, we're always going to graph by increasing values of t. It used to be that we would always graph increasing values of x, like from x is -2, -1, 0, 1, 2. But this time it has nothing to do with the x or y. We're graphing based on the t's increasing. And almost always you're going to start at t equals 0. Almost always. It's not that negative time can't exist, because doesn't negative time just mean like, oh, hey, a second ago or an hour ago, 3 hours ago in the past? So you could put negative time. It's what was happening in the past. You could, if it was something that was being recorded, you could go back and look. So 0 is just a beginning time, but I guess you could go negative, because if you were trying to think back or look back at what was happening before. So 0 is our reference point. This is time that's in front of that or forward from that, and then negative time would be time that's backward from that. And then once we have our t's, we can just plug into our function of t for x, our function of t for y, and then solve, solve, solve. And once you have points, x's and y's, then you're just going to graph them, not just helter-skelter based on any sort of order. You have to go in order of time, because when you go in order from time, you can actually follow the motion, almost always follow the motion of what's going on. So that's why it says plot the points in order of increasing values of t. Start from the left and move to the right, and then in some senses go ahead and connect. Finding the orientation, and the orientation just means the direction of the movement. Now, let's talk about Carl's calculator and the issue that he had, because this is a good time to talk about it. If we just took this and said, okay, to graph, plug in 0, plug in 1, plug in 2, plug in 3, plug in 4, cool. That's what Carl's calculator was doing, and it looked horribly wrong. Let me show you what Carl's calculator was doing. In the window, and this is approximate, Carl, it was a little bit different, but it's the right idea. We'll say that it was going by ones. And that's exactly what this table shows. Go by 1, 0, 1, 2, 3, no big deal, right? Go by 1. So, if Carl's calculator is going by ones, if your calculator is going by ones, you know exactly what the graph is supposed to look like, this spiffy little parabola. But let's check out what's going to happen if you go by ones of this guy. That's not very nice. And technically, if I show you what Carlos was actually doing, he wasn't going all the way to 2 pi. He was going like the actual book or the example in the notes showed us to go to, what was it, 2.2 or something like that?
2.121320.
Yeah, 2.12. So he was trying to do exactly what it showed, so the 2.12, yada, yada, yada. And he just accidentally, instead of putting 0.13, he accidentally put 1.3. So check it, kiddos. If you're only graphing the motion from 0 to 2.12, and you plug in 0, you plug in 1.3, and you're supposed to plug in 2.6, how many steps have you taken? How many positions have you checked? Like 2. You've only checked like 2 positions. Is that going to be a very good picture for your graph if you graph based on t? No. And the reason yours went down, Carl, was because remember the inputting thing was kind of funny. But that doesn't show a great picture. But think of what the calculator's doing. T is time. So when you're telling it, hey, I want you to graph from t equals 0, stop when t equals 2.12. And by the way, only plug in every 1.3. You're only telling it to plug in 0, plug in 1.3, and then it's like, well, I'm done. And so that connects the 2 points, and you're like, well, that's a horrible picture. It's supposed to be a parabola. So instead what we do with the t-min, t-max is we need to go ahead and say, okay, I think I want a little more time, which you could do. They had you stopping at 0, but you could put a little more time, like 3 or 4 or 5. But just because you make it go farther doesn't mean that it's going to look any better. How can I make it a better picture? Instead of taking big steps and saying, hey, what's going on if after 1 second it's there, 1 second it's there, 1 second it's there. The motion wasn't linear. So we could go ahead and check in more often, or we could go ahead and take babier steps. You've seen What About Bob? That makes a little more sense. If you haven't, then never mind. But you could go by 0.1 instead of 1s. How many steps would be in between 0 and 5 though by 0.1s? All kinds of steps, right? Yeah, 50 steps. So therefore, hey, it's going to connect. Can I see my motion better? Yes. So depending on the situation, depending on the times that you're looking at, you might not always want to go by 1s. It might give you a very disjointed picture. And maybe, I mean, if you guys looked at that one, even though it was kind of like linear and segmented and kind of messed up, you still probably would have guessed it was a parabola. But there are ones that get really messed up depending on what you're doing. Actually, can I give you an example? Nah, it'll be better in the next section to give you an example of one that goes super crazy. But we can plug in t's, just be aware that depending on the t range, depending on the t min, t max that you're thinking about for the situation, it might be wiser to take babier steps than just 1s, okay? So, by hand, you can do it in your calculator after if you want. By hand, graph me that parametric. It's kind of basic, it's kind of algebra 1-ish, but for parametric equations, not just functions. And if I were you, just because you're starting off, let's just plug in whole numbers. I know the range isn't super huge from -2 to 3, but let's just plug in the whole numbers and let's see if it's enough of a picture to figure out what the path looks like. Let's see if it's enough of the picture to see what the path looks like. If it's ever not enough, just go by smaller increments. Let's see what's going on. Wow, this is such a mess. I can't kind of see that. So quick recap, you're plugging in the t's, you're getting xy's, you're plotting those xy's, and trying to think, okay, if these are the order of how the positions are changing, and if I was to follow that motion, can I see the path, and can I show the direction arrow, the orientation of the movement itself? All right. What'd you guys do? Does that look pretty good as far as plugging in? And as you were plugging in, remember the t's don't go on the graph at all. Just take the x's, take the y's, and graph them. So my first point, or the first point when t equals -2, which we chose based on this little interval. Right over there. 0, -1. Okay, got it. -3. -1/2. Got it. 0, -4. Okay, got it. negative 3, 1/2. Oh, that's weird. This isn't a function. Travel to the sideways one, huh? Then 0, 1. And then 5. Plus 3 halves. From the points, do you think you guys had enough information to see that? Then how did you put the orientation arrow? Well, you followed the points, right? And as you follow the points, you were tracking the position. So if something was here, then here, then here, then here, then here, we would assume, wasn't it traveling in this orientation on the graph? Does that make sense? You're just showing, hey, it was headed this way. Why? Because in parametric mode, it could have been headed the other way. When we graphed in function mode, we always could look at the graph and say, oh, you graphed from left to right. That's just how it happened because everything was based on x, and x is left to right. But now that t is the guy in charge, I could very well have something traveling backwards just as much as I could have it traveling forward. So what's nice about parametric equations is not only can you graph non-functions, which was impossible in function mode, without putting lots of different pieces together to make them look like non-functions. Not only can you graph non-functions, number one, but number two, you can show going both forwards and backwards on paths where we couldn't have done that in function mode at all. Since t is the main guy, there are definitely some changes that have been made. And why did I not show arrows going on forever? It was bound by the time. I only wanted from negative 2 to 3, and this was the movement and the path of the actual figure. Now, if you were a skeptical person, which you very well might be, and if you're like, well, how do I know it went straight from here to here, and from here to here, and here to here, and here to here? Okay, well, maybe we better learn how to deal with these a little bit better than just guessing by just taking little snapshots. Because technically, could this, for a different pair of equations, could this have done this weird little like boom, ba-doop, 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 and gone all over, then gone here, then boop, ba-doop, 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 then gone? Yeah, it could have, technically. Now, if you graphed it in your graphing calculator, and instead of going by ones, if you had gone by 0.1s or 0.01s, then you would have been for sure like, man, I am tracking this guy every step of the way. Maybe how some of your parents have your location shared with them so they can check you at every single point of the way, because maybe it's not that they don't trust you, maybe that they care, and that's a good thing. But they could look and they could literally follow you to the store that you're supposed to be going to pick up something, and then literally follow you back, right? That would be like checking in at all these different times. Other parents are like, just tell me where you are, when you are, and it's like 5 hours later they have no idea where you've been, even though hopefully you have integrity and you and your parents have a good relationship and you've been honest with them. But anyway, moving on. They're there because they love you. They're checking on you because they love you. If they don't check in on you, maybe they need to. Anyway.
Dude, I want.
Go ahead, and you don't need to write down the 2 equations, but I do want you to write down the little note that we're going to make. Don't write down the 2 equations, but do write down the note. There's just a point to be made on these 2 graphs. Because if you look at these 2 graphs, freshmen, sophomores on. It's noisy. It's right near your break. Probably just someone got left out right after. The idea is, what's also new in parametric is you can have the exact same path, but different parametric. That's something else that's crazy. You can have the exact same path and yet have the equations be different. Now the crazy thing is, they're really not that different. And so since we only have a couple minutes left, I'm not going to go into any more notes, but let me show you kind of where we're going as far as maybe letting you get a little further in on homework. We've talked about how to think about parametric equations in the graphing calculator and with the table by hand. But some of you in that last example realized, well, how do I know for sure it went from here to here? See, you're skeptical too, not just your parents. So anyway, coming back. What we can do is try to ignore the timing and try to get back to the path itself. Because remember, if we can get it in terms of y equals f of x, if we can get back to rectangular, we can see the path, because we're so used to parabolas and cubics and linears. Like, if we can get the path without the t's, it'll make so much more sense. And how can we do that? Well, we could go ahead and do something like solve the x equation for t. Solve the x equation plus the 4 plus or minus square root both sides. Solve the x equation for t and say, well, this t guy, he's messing everything up. Okay, solve for him, and if you solve for him in one, what can you do in the other? Plug him in, you can get rid of them. And you can get the parametric equations into rectangular. The timing has just been completely disregarded, which is also dangerous, but it's another life lesson for another day. The timing has been completely disregarded, and now all of a sudden, you have the path. And maybe the path isn't super clear as to what's going on, but if you were to go ahead and do just a little bit of math, maybe it would make a little more sense why the, well, squared is positive anyway. Function is what it is. Sideways parabola, centered at 0, -4. I think this is going by 2's, right? 0, -4, and facing to the, if we can get rid of the t's, we can say, oh, hey, it is that path. I was right. Dun, 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 dun. It's called eliminating the parameter. Take it out, t. Bye, cool kids. Great job. You can probably start homework and get fairly far. Oh, they should be done. Yeah, anything on the ground should be done. Sorry, guys. I don't know why I didn't put it up at the front. I'll check your grades too, but.
There's still like little red marks. Does that mean it's graded?
Are you serious?
Yeah.
Why is it on the ground here? Oh, someone moved it off my desk. A non-TA. Finish. Let's just go up. They won't be done by lunchtime. And I'll be at the front.
Guess I'll come back after school.
Thanks for checking it back. Honestly, too.
Thank you, Miss D.
Welcome, guys.
Yesterday? Because I ended up leaving it in the